All right, good morning, everybody. Welcome. Happy Tuesday. So we're almost there. Made it. Last week of classes. I guess there's a Monday next week, but not for us. We still have more material to get through. 2 more classes, 2 more big topics. So, yeah, try and keep focused, keep pushing hard all the way through. Don't let up now. Quick note about grading. I'm aware that we're behind. Bit of a delicate subject, but you know, the graders are people too. The graders are students like you. They're also at this point in the semester, they're also trying to just get through this last week. And the thing about grading is you can make it go faster, but then the quality goes way down, and we don't want that. So the graders are aware that we want results, but we also want them to take their time and read your arguments carefully and think carefully about them. I can guarantee you that we will have test 4 scores back to you before the VW deadline, which is next Monday. I'll finish them up myself if I have to. We'll make sure we have you test 4. We're also really trying to get you test 5. So even the instruction staff is helping to grade test 5 to make sure we get that back to you as quickly as possible. I did a bunch of grading yesterday because we know you want all the information possible when trying to make that decision. I know it's not a fun decision to make, but yeah, that's what I'll say about that. Okay. We have warm-up question here to think about. So I've got the set 1, 2, 3, 4, and I want to look at the less than or equal to relation and take a look at that digraph. So I've got to take out a marker. There we go. Got 1, 2, 3, 4. And I want to draw an arrow from A to B if the coordinate pair AB is in the relation. So what's one arrow that I want to draw? One, 1. Good. Nice solid bet. 1 less than or equal to 1 is true. So 1, 1 is in the relation. And every item gets an arrow to itself. That is true as well. Everything is less than or equal to itself. Okay. Good. So now what else do we have? What else is less than or equal to something else? 1 is less than or equal to 2. So I want to draw an arrow from 1 to 2. And 1 is less than or equal to 3. So I want an arrow from 1 to 3. And 1 is less than or equal to 4. So I want an arrow from 1 to 4. Need a couple more arrows. Two goes to 3 and 2 goes to 4. Here's a fun little exercise. How can I end up drawing this graph planar? I'm going to sneak this one around this way. Then 3 goes to 4 is my. So I have an arrow from A pointing to B. Means in this case, A less than or equal to B. Because that's what my relation is. Okay, let's try and work out some of the properties of this relation. So is this relation reflexive? Yeah, right? Reflexive means for any element x, x comma x is in our relation. In this particular case, that means any number is less than or equal to itself, which is true. Or if we look at the digraph, it means every element has a loop, which is true. So yes, we are reflexive. Are we symmetric? One no, one symmetric, many no's. Okay, good. Why are we not symmetric? I agree, but no. Yeah, our arrows only go one way. If we have a symmetric relationship, then if there's an arrow from 1 to 2, it would have to go back from 2 to 1. Or I have this arrow from 1 to 4, but I have no arrow back from 4 back up to 1. Not symmetric. What about anti-symmetric? Yeah, good. I do have anti-symmetric because symmetric requires arrows to go back every time. But not only is it not the case that I have arrows that go back every time, I never have arrows that go back. And that's what we need for symmetric. Symmetric says if A is less than or equal to B, then B is not less than or equal to A, unless you happen to pick the same thing twice. You're allowed to have loops, but if I have two different elements, one of them has to be in the relation, one pair has to be in the relation. At most, one pair can be in the relation, is what I want to say. We can't have both ways. We can't have two arrows. And since we never have two arrows, we are anti-symmetric here. Now, how about the harder one? Is this transitive? Yeah, right? So transitive is one where we need to look at three elements all at once. So I have an arrow from 1 to 2. I have an arrow from 2 to 3. Transitive says I need an arrow from 1 to 3, and it is there. It's really hard to check if a relation is transitive just from the digraph, because you sort of need to check every group of 3 vertices. Right? It's sort of easy to see for symmetric or anti-symmetric. I just look at any 2 vertices and see if there's arrows pointing both ways. You got to check it for every pair of vertices, which is a lot of pairs, but it's easy for me to just look at pairs and check that. Transitive's a little bit harder. It's a little bit harder to think about every 3, right? If I didn't draw in this arrow, it'd be really easy to fool myself. 2 to 3, 3 to 4, miss that there wasn't anything from 2 to 4. But since I know what the less than or equal to relation is, I know that if A is less than or equal to B and B is less than or equal to C, then is A less than or equal to C? Yeah, of course. Right? That's how less than or equal to works. I'm familiar with that. So from last time, what do we call relations that are reflexive, anti-symmetric, and transitive? Partial order. Good. So less than or equal to is a partial order. The symbol for a relation that is a partial order is based on the less than or equal to symbol. Because less than or equal to is a partial order, in fact, it's sort of the the stereotypical partial order. It's such a nice partial order, right? You can think about, if I added more elements to this, what would my digraph look like? Well, I would just sort of keep extending it down, keep adding arrows pointing down. Everything has a loop. It's a really nice partial order. So if fancy R, I'm going to try and do this once. Sort of like the R that we can use when we're typesetting things. A little bit harder to do with Sharpie. But if fancy R is a partial order, we often use the symbol it's like a less than or equal to, but instead of a nice sharp angle, it's like a curly angle. Also a little bit hard to draw with a Sharpie. But that's the symbol we use that you might see. So let's look at a partial order that's not just a nice, simple less than or equal to. I want to look at the set ABC. And its power set. So here's the power set of the set A, B. So this is the set of all subsets. And then I want a relation on this power set. So the two things that go into my relation are both sets. And I'm going to say A is related to B. It's the same thing as A comma B is in my relation. It's often a different color. ARB is just another way of writing A comma B is in our relation. If B is a subset of A. Okay. So let's draw the digraph diagram for this as well. So I need my power set of my set ABC. How many elements are there in the power set of a set with 3 elements? I know ahead of time if I have them all or not. Good. There are 8. For each element, I decide in or out. That's 2 options times 2 options times 2 options gives me 8 options. So I've got the set containing all 3. And then I have the set containing A and B, set containing A and C, set containing B and C. And I'm drawing these in a suggestive order. And then just A, just B, just C. And then I also have the empty set. Oops, I'm off the bottom of the page. Sorry about that. Okay. And so now I want to draw an arrow from A to B if B is a subset of A, right? So we got to make sure, we get our arrows correctly. Arrow from A to B, ARB, so from A to B, if B is a subset of A. So I know that A comma B is a subset of ABC. So I draw an arrow from ABC back to B. Okay. The way that I've worded this here, ARB, from A to B if B is a subset of A. Or you can think of it as if A contains B, then ARB. Okay. So also ABC contains itself, and ABC contains AC, and ABC contains BC, and ABC contains A, and B, and C, and also the empty set. It's starting to get messy. Do another color. We also have AB contains A, and B, and the empty set. And running out of colors here. A contains the empty set. There's a lot going on here. You can see I've only done, missing some still. Also, AB has an arrow to itself, and A has an arrow to itself. And also the empty set has an arrow to itself. And I've only done half the diagram, and already it's pretty hard to read. If I asked questions, like if I did the whole diagram and I asked, is it reflexive? It's pretty easy to check each thing one by one and check if it's reflexive. But if I want to ask symmetric or anti-symmetric, it's going to be really hard to follow all the arrows, let alone transitive. Transitive is going to be crazy. So let's think about this question. And I've sort of given it away because I said that we're going to look at another partial order. But let's think about this question just in terms of this relation less than or equal, or subset of. Is this reflexive? Is any set a subset of itself? Yep. We do have reflexive. Is it symmetric? No, not symmetric, right? If B is a subset of A, then A is not a subset of B unless they're equal. So it's not symmetric, but it is anti-symmetric. I have no idea how to spell anti-symmetric. Probably not two S's. Probably just one S. And we do have anti-symmetry because for that very reason, if A is a subset, if B is a subset of A, then A is not a subset of B unless they're equal. And do we have transitive? Well, if C is a subset of B and B is a subset of A, do a little bit of set theory. Everything in C is in B, everything in B is in A, so everything in C is in A, so C is a subset of A is true. But yes, we do have transitive. And we do have a partial order. And since we have a partial order, there's another way I can draw this diagram. So I've drawn this one all nice and large to make sure we could fit in as many arrows as I could. But I'm going to squeeze another diagram into this little space here. And the idea is, if I know that a relation is a partial order, I can take that into account when I draw the diagram. So this is our digraph diagram that I started drawing. Didn't even finish it. It was just too much. But there's another type of diagram called a Hasse diagram. H-A-S-S-E. And the way the Hasse diagram works is I already know that you can only draw a Hasse diagram for partial orders. You have to be reflexive, anti-symmetric, and transitive. I already know that every element's related to itself. So I don't have to draw these loops. That's just wasted space. I'm going to skip the loops for partial orders. Skip the loops. You can also skip the arrows. When you're drawing in Hasse diagram. And then lastly, we know that certain edges have to exist by transitivity. So we're going to skip the transitive edges. So let's look at the Hasse diagram for this partial order. Skip the arrows, just like that. And it is true that ABC contains A, but AB also contains A. And so the line from A to ABC is implied by transitivity. So I don't have to draw it. A is also contained in AC. AC also contains C, and B and C. And AB also contains B. And A, B, and C all contain the empty set. But all of the other arrows are just implied in the Hasse diagram. Right? I don't draw it from ABC to the empty set because that's implied by transitivity. There's an implied arrow from ABC to C, and then there's an implied arrow from ABC to empty set. So this is a much nicer diagram for partial orders. And so if we come back, we can even draw the Hasse diagram for our less than or equal to. On our set 1, 2, 3, 4. So what's that going to look like? We've got 4 at the top. 4 is greater than or equal to 3. 3 is greater than or equal to 2. 2 is greater than or equal to 1. Right, a really nice, simple, compact way of expressing what's going on. Questions? How do we feel these Hasse diagrams? I just want to work from these going forward. So if I look at these two diagrams, even before I define anything, if I say I want to talk about a maximal element, in each of these diagrams, which one do you think is the maximal element? Yeah, right? ABC should be a maximal element. 4 should be a maximal element. The Hasse diagram makes it really nice. The maximal elements should be at the top. That's where they should be. So let's define maximal and also minimal, keeping in mind what this definition is going to mean. Maximal is going to mean it's at the top. Minimal is going to mean it's at the bottom. Okay. So in a partial order, a maximal element A satisfies A less than or equal to B implies that B is equal to A. It's not true that maximal elements are not less than or equal to anything. I should really use curly less than or equal to here, because this is for a general partial order. It's not true that a maximal element is not less than or equal to anything. It's true that the only thing it's less than or equal to is itself. And a minimal element is the same, except the only thing it's greater than or equal to itself is itself. And a minimal element, Z, satisfies if Y is less than or equal to Z, then actually Y was equal to Z to begin with. That's the only way you can be smaller than a minimal element, is if you are yourself minimal. Okay. So now that we have Hasse diagrams, I can draw partial orders much easier. I can give you examples of partial orders much easier. Here's A, B, C, D, and E. These are 5 elements I have in a set, and here's the partial order on them. Okay. So let me ask you some questions. So this is a partial order on the set A, B, C, D, E. All right, so does this partial order have any minimal elements? Yeah, good. Right, remember our intuition. Minimal elements should be at the bottom. E is at the bottom. E is, there's nothing less than or equal to E except for itself. Good. Also, quick question. Is E curly less than or equal to A? Yeah, right, good. Equivalent question, is E A in my relation? And the answer is yes. I didn't draw an arrow from A to E because there's an arrow from A to C, or a line from A to C, and a line from C to E. And so I don't need to draw anything from A to E directly. It is implied by transitivity. Does this partial order have any maximal elements? Good. I have two maximal elements. Both A and B are maximal. Both A and B have the property that they're at the top. Nothing is above A or B. So you can have more than one maximal or more than one minimal element. That's okay. Maximal just means there's nothing above it. Minimal means there's nothing below it. That's different, and for non-English speakers, and even for English speakers, I apologize for this, but this is just the way it is. That's different than a maximum or minimum element. So I'm going to define those next. A maximum element satisfies B is less than or equal to A. A maximum element A satisfies B is less than or equal to A for every B in my set. This is a partial order on A. And a minimum element is the same, but for being small. A minimum element, Z, satisfies Z is curly less than or equal to Y for every Y in A. So next question, does this partial order have a minimum element? Yeah, E is not only a minimal element, it is also a minimum element. E is less than C, E is less than D, but E is also less than A by transitivity, and E is also less than B by transitivity, and E is always less than or equal to itself, because partial orders are reflexive. So E is a minimum element. Do I have any maximum elements? Yeah, all right. I don't have any maximum elements. There's no element I can point to that's above everything else. A is above everything except for B. B is above everything except for A. But there's nothing that's above everything altogether. So, difference between maximum and maximal elements. This partial order has maximal elements, no maximum element. Also a difference between minimal and minimum, although in this case E is both. So it's possible to be both. Want to think about that just a little bit more. Get a theorem out of it. if I have a maximum element, that maximum element must also be maximal. So let's think about why. We have an element that's greater than or equal to everything else. Is there any chance anything is bigger than it? Well, no, then it wouldn't be a maximum element. How the proof is going to go. Let A be a maximum element. Then for all B in A, B is less than or equal to A. That's what it means to be a maximum element. So now suppose that A is less than or equal to B. We know B is less than or equal to A. So if A is also less than or equal to B, since our relation is a partial order, it is anti-symmetric. So A must be equal to B. The only way B is less than or equal to A and A is less than or equal to B in an anti-symmetric relation is if they're equal. Therefore, if A is less than or equal to B, B is equal to A, so A is maximal. And we have another theorem, which I'm not going to write down the proof for. Good exercise. Write down the proof of this theorem. If Z is a minimum element, then it is minimal. And you can think of basing your proof off of this proof. You should be able to write a proof of this theorem. One more pair of theorems I want to talk about before our break. I've been very careful to say a minimum or a maximum element, but your intuition might tell you that there can only be one. So let's write that down and prove it. If a partial order has a maximum, and then in parentheses I'm going to say or minimum element, then there's only one. You can't have two maximum or two minimum elements. It is unique. Okay, before I write down the proof, any guesses of how I'm going to prove this? Any ideas for how to start a proof like this? Yeah, really good. Show that if there are two, they're equal. We can do this by contradiction. We don't have to. We can see, so I'm going to write this proof without contradiction, and then I'm going to talk about what it looks like with contradiction and see how they're very closely related. Both are correct. As mathematicians, we tend to prefer not to use contradiction if we can avoid it. Contradiction is just like a little twist on a proof that makes it a little bit harder to understand, right? You're assuming something that's not true, and then it ends up causing a problem. If we can get away without that, it's better. So I'm going to do this without. I'm going to say assume, not for contradiction, just assume that A and B are both maximum elements. So since A is maximum, B has to be less than or equal to A. And since B is maximum, A is less than or equal to B. And because our partial order is anti-symmetric, that must mean A is equal to B. Only way you can have this going in both directions is if they're equal. So you can definitely think about how to turn this into a contradiction proof. You assume for sake of contradiction A and B are different maximal elements. And then if they're different, you can't have A less than B and A less than B and B less than A. But we've gotten around that contradiction proof. We're just saying, okay, take any two maximum elements. Oh, you chose any two and they happened to be equal. That must mean there's only one. That must mean it's unique. And the proof for minimum is very similar. Take two minimum elements, one's less than the other's less than the first, so they're actually equal. Questions about any of these theorems or their proofs? If not, let's take a break. 2 minutes. Get up, stretch, refocus. We'll come back. 9:17. Big time. Yep. Curly A curly less than or equal to B means that A comma B belongs to the relationship curly. This is based on the less than or equal to symbol, because partial relations act like less than or equal to or greater than or equal to. But we just picked one, and we picked less than or equal to base the symbol off of. There is a similar curly greater than or equal to symbol. I really struggle with drawing that one. Yeah, I said 9:17, but I meant 9:18. 9:17 would only have been a minute and 10 seconds. Okay. 9:18, let's come back. Let's refocus, regather. Interesting question for you. So, part A, can you draw a Hasse diagram for a partial order with no maximum or minimum element? And part B, can you come up with a partial order with no maximal or minimal elements? What do we think? Because it's hard to draw things in chat. This is where, if we were in class, I'd invite somebody up to the board to draw a Hasse diagram. But any ideas? For either one of these? Well, we saw an example without a maximum. Yeah, right, similar to this, but let's add an F. So I can have an A and a B. Neither one of these are maximum. A C and a D. And now instead of just an E, I'm going to have an E and an F. And I can add edges here, here. And I can even add edges here if I want. Let's see. And then something like that. I have no maximum element because nothing's above A and nothing's above B, but they're not above each other. And I have no minimum element because E and F are both minimal, but nothing's beneath the other. So A, I can do A for sure. What about B? We come up with a partial order with no maximum, not only no maximum, no minimum, but no maximal or minimal elements. So let's think about what that would look like. We have some element in the middle. It's not maximum, so there's something below it. But it's also not minimum, or it's not minimal or maximal. So if it's not minimal, then there's something above it. If it's not maximal, then there's something below it. And then I can apply that same reasoning to this element. There's got to be something above it. And there's got to be something below this one. You think of a partial order that would have a Hasse diagram that looks like that. What do we know about the number of elements we need? Yeah, right. We need an infinite number of elements. Need to keep going up and up and up forever, and also down and down and down forever. So can you think of a set that goes infinitely up and infinitely down? Real numbers are interesting. So integers was what I was going for. This is going to be the Hasse diagram for the integers on the relation less than or equal to. Right, you can put 0 right in the middle, and then 1, 2, 3 all the way up, and -1, -2, -3 all the way down. Real numbers is not a wrong answer for a very hard to see reason. The problem with the real numbers is I can make this one 0, but what do I make this one? There's no first real number after 0. So in order to use the real numbers here, you need an ordering on the real numbers with like a smallest, or with a so you need to put them in an order, right? Because r is uncountable, we have this problem of writing this out in this way, right? So it's like yeah, right. If you put a restriction on the number of decimal places, then you can do this. Using r here is just a really interesting question that I wish I had more time to get into. Take a set theory course is what I'll say if you want to learn more about that. But okay, I'm going to move on. Integers z and less than or equal to is a good example. That one has no maximal or minimal element. There's no biggest integer. There's no smallest integer. It's also true for real numbers, but it's a little bit harder to draw the real numbers in the Hasse diagram. I guess I'll say that. Okay. If I look at a Hasse diagram, I'm also interested in something called the greatest lower bound and the least upper bound. So here's a Hasse diagram. And if I take two elements, I guess I should label these. So let's call this A, B, C, D, E, F, G. The least upper bound, sometimes LUB, of two elements X and Y is an element Z satisfying two things. Property 1, it has to be an upper bound. So X is curly less than or equal to Z, and Y is curly then less than or equal to Z. That's what it means to be an upper bound. But also it is the least upper bound. So if I have any other element that does this, if X is curly less than or equal to Z prime, and Y is curly less than or equal to Z prime, then Z is also curly less than or equal to Z prime. This is what it means to be the least one. Might not be the only upper bound, but it's smaller than any other upper bound. It's smaller than any upper bound. So, and then I guess I'll say the greatest lower bound GLB is similar. You're just going from below. Okay, so I just want to get some practice with this. What is the least upper bound of B and C? D. Yeah, good. The smallest thing that's bigger than both B and C is D. So it's a good question. Is D both the least upper bound and greatest lower bound? It depends on what I'm talking about. Right? So D is the least upper bound of B and C. What is the greatest lower bound of B and C? That one's A. A is the biggest thing that's smaller than both B and C. A is also the only thing that's smaller than B and C. But D is not the only thing that's bigger than B and C. What else is bigger than B and C? G and also E and F. E, F, G, and D are all upper bounds for B and C. Right? Remember transitivity. But the only one that's the least upper bound is D. Okay, here's another question. What is the least upper bound of F and D? I fooled you. This is why we do practice during lecture. The answer is not G. I'll give you that hint. It's not E, because E is not greater than or equal to F. So, okay, let's go through some things. It's not E, because E is not greater than or equal to F. And it's not G, I'm claiming, even though G is definitely an upper bound for both. G is bigger than F, and G is bigger than D. So, unless I'm lying to you, if G is an upper bound, but is not the least upper bound, what does that mean? Yeah, exactly right. Ashley's got it. F is the least upper bound. Because F is bigger than D, and every element is bigger than itself. Remember, we're in a partial ordering, which means we always have reflexivity. So D is less than or equal to F, and F is less than or equal to F, which means the least upper bound of F and D is F itself. And the reason it's not G is because of this second property. It has to be the smallest upper bound. And F is smaller than G. F satisfies both of these properties. D is less than or equal to F, check. F is less than or equal to F, check. And G fails on this property because G is not less than or equal to F. So that is the tricky part about least upper bounds. One more thing I want to add to this. Just going to add another element h, so that I can ask. Everything I've written is still true, by the way. What is the least upper bound of G and H? Is there any element that satisfies these two things for G and H? So there is not, right? Nothing is bigger than both G and H. So it is possible that least upper bounds and greatest lower bounds don't exist. That is a thing that can happen as well. Wanted to make sure I mentioned that. Okay. One more thing to talk about today. Got 10 more minutes. Shift gears a little bit. That's all of our partial order stuff. We talked about another special type of relation, and that was the equivalence relation. So R is an equivalence relation. If R is, we said, reflexive, symmetric, and transitive. So let's think about what the digraph diagram for a equivalence relation might look like. So first of all, everything always has a loop to itself. And then if I ever have an arrow from A to B, I need that arrow to shoot back to A as well. And if I ever have an arrow from A to B and B to C, well, then I also need an arrow back from C to B. But also now I have an arrow from A to B and B to C, which means I need an arrow from A to C. And again, symmetry says I have to go back. And then maybe if I choose to add an arrow to D, well, it's got to go back. But also now I have an arrow D to C, C to B, so I need one B to D, and back. And I have an arrow A to B, B to D, so I got to go around, come back. Or I might have stuff that's completely not related. I might have another thing going on over here. But in the digraph of an equivalence relation, I either have a complete digraph. I have every possible arrow between two vertices in some component, or they're disconnected. Right? In an equivalence relation, there's no way to get from D to E unless everything is super connected. So if I added one more arrow here, if I added one arrow from D to E, that would require tons more arrows. E back to D, but also everything over here would have to get connected to everything over here in both ways. And so we call these two groups equivalence classes. And here's the big theorem. We talked earlier about partitions, right? Taking a set and breaking it up into different subsets so that every element appears in exactly one subset. You're basically breaking it up into groups. An equivalence relation always gives you a partition, and every partition is an equivalence relation. In some sense, equivalence relations and partitions are the same. Here's our big theorem. For any set A, an equivalence relation this is the symbol we normally use for equivalence relations. It's a tilde. Equivalence relation tilde on A induces a partition with the sets of the partition equal to the equivalence classes of tilde. And any partition induces an equivalence relation. When I say induces, I just mean if you give me a partition, I can find an equivalence relation that's like created out of that partition. Where A is related to B if and only if A and B are in the same part of the partition. Okay. So, got 4 more minutes in class. I just want to do a quick example of this. If I take the numbers 1 up through 10, I can partition them, let's say, based on the number of factors in their prime decomposition. So I'm going to break this up into 1 has no prime factors, so it gets to be a set all by itself. And then the prime numbers get a group. 2, 3, 5, 7. That's all of them. And then the numbers with 2 prime factors get a group. Use that color. So 4 is 2 times 2, 6 is 2 times 3, 9 is 3 times 3, 10 is 2 times 5. And then the numbers with 3 factors, which is only 8, also get their own group. Am I missing a green? So this is a partition. And this partition tells me about an equivalence relation. So I have the pairs. Twiddle has the pairs 1, 1. And then any 2 of these, including repeats. So 2, 2, 2, 3, 2, 5, 2, 7, 3, 2, 3, 3, 3 comma 5, 3 comma 7, and so on. And then I get the teal pairs, 4 comma 4, oops, 4 comma 6, 4 comma 9, 4 comma 10, 6 comma 4, 6 comma 6, and so on. And then at the very end I get 8 comma 8. And that's guaranteed to be an equivalence relation. It's guaranteed to be symmetric, reflexive, and transitive. And so anytime you have a partition, you have an equivalence relation. Anytime you have an equivalence relation, that gives you a partition as well. And these two are deeply related concepts. I will stop things there, hit the end of class. But yeah, so see everybody on Thursday for our last class of the semester. It'll be sad, but we'll wrap up. We'll talk about modular arithmetic then, and yeah, I'll see everybody then.